mentioned that's not yesterday, right?
I'm pretty confident in a lot of things I do. That is not one of them. There's a reason that the Netherlands is not known for great dancing. All right. So the sine, and what does it look like? And so here's a different way of looking at it. If you have a circle, and this is called the unit circle with the equation over here. If you remember back, we've done this before. So if I make this side 1, and that's what makes this a unit circle, okay, what would be the sine in terms of the x and the y coordinates of this particular triangle here, if I make this a right triangle? Okay, so the x would be here, correct? So the distance from here to here is x, and the distance from here to here is your y value. Is everybody with me there? So what's the sine of theta? Just in triangle terms, the sine of theta would be y over 1, opposite over hypotenuse. And y over 1 is y. So in essence, what I'm trying to tell you here is that if you can find the height for the point, then that is the y value you need for your sine. So if you're here in your rotation, then this y value becomes the height of the sine function if you graphed it on a rectangular coordinate system. So do you guys sort of see how these connect? So like over here, when you're at this point here at 90 degrees, and you know, for example, you know that the distance is 1, right? So the coordinates here would be what? 0, 1. So that's why at 90 degrees your sine is worth 1. Okay, and we've done this before. We did this a while back. We just I didn't call it the unit circle, but it's known as the unit circle. Okay, so the other thing is what they did here is in terms of the angles, they did not use degrees. Now we did degrees yesterday because it's just easier, I think, for most of us to think in terms of degrees, but they did pi over 6, pi over 3, pi over 2. So those are just the radian measurements that we need to graph this thing. Okay, well, if I know that I get this pattern anyway, guess what you get to eliminate in terms of if you made a table for this? So I'm going to cross off all the things that I don't need. I don't need this one. Don't need that one. Don't need this one. Don't need that one. Or this one. Don't need that one. Or this one. So here are the dots that I'm going to put in the table. 1, 2, 3, 4, 5. Other than that, what do you know? Well, it's a smooth curve that looks like this. It's a wave. So you don't need anything else when you set up a table. You guys sort of okay with some sort of front loading here? So this is what's going to happen. Are you sort of okay with the picture here and how that we're going to be able to make a nice looking curve just on those dots? All right. And then the other couple things that are important to notice, which are underneath here, is that you know, the highest you ever go is 1, the lowest you go is -1, and that was in the bell work. But that means that the range for the sine is, and this is the way that you could write it, from a -1 to 1, including those. I also asked in the bell work about, well, what if the values are larger than 2 pi? Keep in mind that 2 pi is worth how much in degrees? 2 pi is 360, right? So this was another bell work question. I asked you, well, what happens at 390? Well, the pattern's just going to continue. So the pattern continues here, and the pattern continues over on this side. Okay? The distance from here to here, that is what's known as the period. So the period is how long does it take to cycle through all your values. Well, if you start at 0 and you go to 2 pi, the distance between 2 pi and 0 is, well, it's 360, but I want to do this in terms of radians, so it's 2 pi. That is how you find the period. You find the start and the end point, you subtract them from each other. And that's it. Okay, so now let's look at some examples. So how do I graph this particular function? Okay, so step 1 is to find the period. So I'm going to rewrite this slightly. I'm going to say that's sine times 1 times theta. So normally the period for a sine is 2 pi. That's sort of what I said. Well, in this case, if you divide by 1, the period still is going to be 2 pi, right? You guys okay with that? And you'll see me do this again. So, right. So the next step is to figure out what you count by. So I'm going to scoot back just a second, and I'll try to show you with some arrows what I mean with count by. But I'm going to clear this whole slide here, if I can figure out what my... Alright, erase all incoming slides. So the count by refers to this. And I do need these gone, so I don't want those, I don't want those, I don't want those. Alright, so if I start at 0, how many steps does it take to go through your whole cycle? So 1, right? Here's the second step. There's my third step. There's my fourth step. So what I really want to do is divide the period into 4 equal parts. Okay, so I want the period, but I want to split it into 4 equal parts. Well, how do you divide something into 4s? Multiply by? Yeah, but we're doing this with fractions, right? Okay, so you literally, to do the count by, you multiply by 1 over 4. So the count by will be the period times 1 over 4, which would be 2 pi over 4, which is pi over 2. This is what we count by. That allows me to set up a table.
On all your graphs, you have to find out how many sections you need.
Yes. Well, there are always 4. You need to find out how do you make it so that it's equally split into 4 sections. So once you find your period, you just multiply by 1 over 4, and that's your count by. So now I'm going to make a table. And you guys sort of figured this out on your own yesterday. So if you're going to make a table here, theta actually represents sort of your x value, right? Yes? Okay. Now this table will be a little bit different in terms of organization. I'm going to divide my x's here. And this is where the count by comes into play. So we're going to start at 0. 0 degrees or 0 radians. What am I counting by? Okay, so 0 plus pi over 2 is 1 pi over 2. Plus pi over 2 is 2 pi over 2, which is pi. Plus pi over 2 is 3 pi over 2, which does not reduce. That's 3 pi over 2. Plus pi over 2, which is 4 pi over 2, which is 2 pi. Now, I usually don't write these, but I'm trying to show you, why do I not have 2 pi over 2 here? Because it reduces. Why do I not have 4 pi over 2? It's because it reduces. Okay. On your next line then comes the sine of theta, which is what we want to find, and this is like the y value, isn't it? So your y is going to run this way. The pattern for the sine is going to be, it's listed up there, it starts at 0, then it goes up to 1, back down to 0, down to -1, up to 0. I'll let you copy that, and I'll try to show you that what I mean with the pattern on the previous graph. Okay, so it's 0, 1, 0, -1, 0 in that order. Can I move back a second to show you where that came from? So really what I meant was, after you found the count bys, notice that we started 0, so we added pi over 2, plus pi over 2, plus pi over 2, plus pi over 2. So those were the x's in the table, right? And then here is the pattern. The sign starts at 0, it goes to 1, it goes back to 0, it goes to a -1, it goes up to 0. That's the y value pattern. So these are the y value patterns that I just put in the table. Well, that means that I should be able to recreate this graph. Okay, now it says finish the table. In this particular example, there's nothing else to do. So what happens here? Well, you start, sorry, I need to do this. So I'm going to do 1, 2, 3, 4 steps, and it ends at 2 pi, right? And I'm lazy, so I usually mark all of them. So I'm just going to mark the middle one and the last one. 0 is already marked for me. And then you can plot your y values. Where does this thing start? At 0, right? Then it goes up to 1. Put a dot at 1. Goes back to 0. Goes back to a -1. Goes up to 0. And then you just do the pattern as best as you can, which means that you make it look like a nice smooth curve. And you can see I missed my curve a little bit, but this is one reason that I usually dot, so I can cheat it a little bit. And most of you guys had a smooth curve, and yours hopefully will look a little better than mine. So don't make this angular. You're not connecting dot to dot to dot, so you're not connecting it this way. Okay, make these round so it looks like a sine. Okay, that's the regular sine of x, or sine of theta. So we need to make this obviously a little bit more difficult. Otherwise, it wouldn't be any fun. Okay. So here's a cosine example. The steps are the same in terms of what you do. The first thing we do is find our period. And the period for the cosine is also 2 pi. Okay, here is the part where it gets a little bit different. And that would be, this is not just 1 theta, right? This is 2 over 3 times theta. Can I write it that way? Yes? 2 theta over 3 can be 2 over 3 times theta. Okay, then this is just a trick you have to sort of learn. If you divide the period by that number, you will get the new period. So this function will actually not go from 0 to 2 pi. What do you do with dividing by a fraction? You can... Alright, so we're going to do that. Well, that cancels. That actually makes this period 3 pi. So there's the period, 3 pi. Okay, so what was step 2? What do I need to do next? Count by. So you multiply by 1 over 4. Because you want 4 equal parts. And 3 pi times 1 over 4 is? So this is what I count by. Now usually, I don't make a second line usually. So you can just do it this way. Bless you. Okay? Once you find the period and what you count by, you can actually make a table. So I'm sort of on step 3, and the table is going to look similar, but different. It still starts at 0, but what am I supposed to count by?
3 pi.
Okay, so plus 3 pi over 4 is 3 pi over 4. And then I get 6 pi over 4, but 6 pi over 4 reduces, doesn't it? So that's 3 pi over 2. And 6 plus 3 is 9 pi over 4. And then this should be my last step. And what should I end at? 9 pi over 4 plus 3 pi over 4 is 12 pi over 4. And 12 divided by 4 is? 3 pi. So here's a check in your table. If after 4 steps you don't get your period back, somewhere you went wrong. Either you got the wrong period or you got the wrong count bys, or you added your fractions wrong, or something. But you can go back and check. Okay. Now we need to do, and this is takes a little bit used to. So the reason we did this mess is so that I can just write 2 theta over 3 over here. Okay? Alright. Now I got to go back all the way to the first slide. So I'll come back to this in just a second. So let's see if we can figure out, and I erased this, but this is fine actually because I ran out of room. Remember this little triangle here that I made? And this is where x, and this was your y? Yes? No? Yeah? Okay. What's the cosine for theta? Remember, the distance from here to here was 1, right? This is in a unit circle, so that means that the radius is 1. What's the cosine of theta in this triangle? It's x over 1, which is just the x coordinates. So if I'm on a unit circle, then this dot would be represented with 1, 0, right? And this dot would be 0, 1. So let's look at the x values here. How does this pattern start? Because that's what the cosine does. The cosine starts at 1, then it goes to -1, and then back to 1. There's your cosine pattern. It's 1, 0, -1, 0, 1. So that's what you want in this line. You want this to say cosine starts at 1, goes down to 0, down to -1, back up to 0, back to 1. Because you got to start and finish in the same spot. Okay, so I wrote that over here. The cosine pattern is different from the sine. So the pattern, yeah, well, I showed you where it came from, right?
There's only two possible answers, basically.
Yeah, sine starts at 0, 1, and then continue, and the cosine is 1, 0. So yes, and we're only doing sines and cosines this year, so you only have to memorize 2.
Is there a tangent?
There's a tangent and a cotangent pattern. They're different. And then cosecant and secant patterns, and they're different. Sort of. Okay. So what does this graph look like if you now graph it? Again, I don't really need negative angles, right? Because the pattern's just going to continue. We divide it into 1, 2, 3, 4 chunks. That is 2 pi. The middle is at pi. But where do we start? At 1. So we start at 1, down to 0, down to a negative 1, up to 0, up to a positive 1. Now, don't start the line here. This is a pattern that repeats, right? Yes? So notice that, like, to the left of my first dot, it would have gone down. Because both the cosine and the sine, they go from 1 to a negative 1, and then they just oscillate between those two. Okay. That's the regular cosine. I think I got one more, don't I? I think I do, but I know a couple of you are finishing, so now we do need to spend a little time, one more example, so a little more time, because other than changing the period, this graph can also be lifted up or brought down or multiplied, and we already saw the multiplying, for example, with the 2x, or here. But there are some other things that we can do. So is everybody finished? Can I move on? Okay. All right. So here's the whole summary. Okay. And this looks a little funky here. This b times theta, and then this b times theta over here, those things. That was just like, what if it was 2 theta, or what was it, what did we do? We just did 3 theta over 2. So in this case, b would have been 2. In this case, b would be 3 over 2. So I'm trying to give you like a general form. So, but the steps are, find the period by dividing 2 pi by the number on the inside of the function. So we divide by 2, or we divide by 3 over 2. Divide the interval of the period by 4. Maybe I should have said multiply by 1 over 4. So we multiply by 1 over 4. That's your count bys. Make a table, start at 0, and using the equal parts, you go through one period. If it's a sine, you got to start with this pattern. If it's a cosine, you start with that pattern. Okay, after that, you do more, whatever it asks for. So let's see how that works on this one. So step 1 is to find the period. Yep. The period should be 2 pi, but I have a number in front of theta, so what am I supposed to divide by? Nope.
Oh, 4.
It's the number with the theta that you need. And that's why I'm doing this, because sometimes that happens. So then you multiply by? I need to find the count bys, so that's the period. Multiply by 1 over 4, so what am I going to count by? Pi over 8, okay? Remember that when I asked you guys to look at the sine of 2x or 2 theta, you guys all said it will go much faster? Well, don't you think 4 should go even faster? So if the period is supposed to be 2 pi, now it's only pi over 2. That's because this thing is going fast. Okay, and you're not counting by pi over 2s, but pi over 8s because it's going so fast. What's the next thing? So we got the count by. I think we're ready for a table, aren't we? Okay, so theta. The next line over here is going to be the sine of 4 theta. You can already fill this line in, can you not? What's the pattern for the sine?
0.
And then it's back to 0, right? And this is why I said it's a lot of times it's faster to graph it without the calculator, because you already know what points you want. It starts at 0, right? The angle starts at 0. We're counting by pi over 8, so that's 1 pi over 8. 2 pi over 8, but that reduces to pi over 4. 3 pi over 8, and then 4 pi over 8. But 4 pi over 8 is actually pi over 2, which is exactly what you needed, because you said the period was going to be pi over 2. I'm sorry about the crooked line there, but okay, what does the negative 2 do in this particular problem?
Is it being put to the left instead of to the right?
Well, what does the negative 2 do to the sine of 4 theta? Doesn't it just, in terms of, why it's going to flip this, yes. But in terms of mathematical operations, is it going to add, subtract, multiply, or divide it? The negative 2 is going to, isn't the negative 2 in front of the sine of 4 theta, so it's going to multiply? So you literally take the y value that you had and multiply by negative 2. That's still 0. That became a negative 2. That's still 0. That became a positive 2. That's still 0. Okay, so the negative 2 multiplies. Compare that to this one. What if I wrote a negative 2 plus the sine of 4 theta? What did the negative 2 do now? The negative 2 and the sine are adding to each other, right? So, well, it adds a negative 2. So here, it adds, but if you add a negative 2, that actually means you're subtracting 2, right? So we're not going up, that means we're going down. So notice the difference there, okay? One is a multiplier, and you just multiply. The other one would have been, well, add a negative 2. 0 plus a negative 2 would have made it a negative 2, etc. Okay, once you have those, you are ready to actually graph this thing. So this should start to get a little boring in terms of, well, what do you do here? Well, 4 tick marks, borrow the one at the end, copy the one in the middle, and then here it starts at 0, and then you go to a negative 2. Back to 0, positive 2, back to 0. So, and somebody said this earlier, what happened here? What happened actually with the graph of sine of x? Like comparing it to the sine of x, what happened? And I'll draw that in blue real quick so that maybe you can see what I'm referring to. So here's the graph for the sine of x. It does this. What happened? With this being a 1 and that being a negative 1. So this is the sine of x, or theta. What happened? There are two things that happened here. This one goes up first.
Yeah, this one goes down.
So that's called the flip, right? In terms of where that came from, that was that negative. And what else happened? Keep in mind that this is a negative 2 and this is a positive 2. It was multiplied, and that was the 2, right? It was multiplied by 2. No, and I want you to sort of see that so that you're not surprised that it's happening. I think it's important. It's the same transformations that we looked at when we did quadratics, and that's what I'm trying to get at. So I'll spend a little more time on that tomorrow and then the day after. But those are called transformations. So, you know, we start with the sine of x. What does it look like at the end of it? That would be called the transformation. So in this case, there are two things that we changed, sort of. Well, actually 3, right? Because what else happened? I forgot. The first thing that was happened is it was crunched, right? Maybe I should put the one on the same. So here is what this red one would look like on the other one. So it starts at 0, and it goes down to a negative 2. But if this is 2 pi, that's pi. This is pi over 2, right? We okay with that? Yes, no. Okay, this whole graph goes through the whole sequence like that. This is what they look like sort of side by side. If I make that, so that's 2 now, and that's a negative 2. So this is what the real difference is, or this is all the differences. Okay? So it changed the period. That means it went faster. It was flipped, and it was multiplied by 2. So 3 transformations.